Hello, everyone, and welcome. I'm excited to have you here today. We're about to dive into an engaging topic, mathematical reasoning. This is the first slide of our presentation, and I just want to give you a quick overview of what's coming up. We'll explore core concepts, strategies, and applications that will deepen your understanding of mathematical thinking. So let's get started and make this an insightful session. All right, let's take a closer look at the implications of what we've discussed so far. On this slide, you'll see several key topics. First, the concept of a statement, the building block of logical reasoning. Then, moving on to quantifiers, which help us specify and limit the scope of our statements. Next, we have implications, which are essential for understanding logical relationships and cause-and-effect scenarios. We also explore compound statements, where we combine simple statements to form more complex ones, and operations on sets, which are fundamental in understanding collections and their interactions. Biconditional statements are next, representing situations where two statements are equivalent in truth value. Arguments are critical as they involve reasoning from premises to conclusions, and mathematical reasoning ties everything together by applying logical principles to solve problems. Finally, we come to implications again, emphasizing their importance in logical deduction and proof. Throughout this slide, the goal is to understand how these concepts interconnect and support our overall theme of mastering logical reasoning. These ideas form the foundation for more advanced topics and help us think more clearly and rigorously about problems. Let's take a closer look at this statement. Here, the focus is on explaining the key points thoroughly, but in a conversational way. I want to make sure we highlight the most important concepts so they really stand out. As we go through, I'll connect these points to the overall theme of the presentation, showing how they fit into the bigger picture. This approach helps us not just understand individual ideas, but also see how they all come together to support our main message. Remember, the goal is to keep it engaging and clear, so that the audience can follow along and see the relevance of each point. Today, we're going to explore a fundamental concept, a sentence that is either true or false, but crucially, not both. This idea might seem simple at first glance, but it actually touches on some of the deepest questions in logic and philosophy. When we say a sentence is either true or false, we're referring to the principle of bivalence, which is central to classical logic. It means that every declarative statement must have one, and only one of these truth values. Understanding this helps us clarify how we evaluate statements and arguments, especially in complex reasoning. It also connects to the broader theme of how we distinguish between valid and invalid logic, and how truth values underpin our entire system of critical thinking. So, by grasping this idea, we're laying the groundwork for more advanced discussions on logic, language, and even artificial intelligence. All right, let's look at this slide. First, I want to clarify that this isn't a statement, it's more of a reminder. The phrase, "please keep quiet in the library," is a simple rule, but it's a good example to understand how statements work. Now, moving on to the numbers thra, 2, and 1, they're not just random, they're part of a little exercise to challenge our understanding of truth and falsehood. So when we see 10 is less than 1, that's clearly false, because 10 is definitely not less than 1. It's a good reminder that not everything we hear or see is true. Sometimes things are just false. Then we have 10 is less than 11, and that's true. 10 really is less than 11. Finally, the examples part at the bottom is there to show us how to test statements for their truthfulness or falsehood. This is an important concept, especially when we're trying to evaluate information critically. Throughout this presentation, we'll be exploring how to identify statements, and understanding these basic truths and falsehoods is fundamental to that process. All right, let's look at this slide. We're exploring some statements and whether they are true, false, or neither. The first statement is 123 is divisible by 3. Now, since 123 divided by 3 equals 41, which is a whole number, we can say this statement is true. Moving on, the second line is blank, which reminds us to pay attention to missing information or incomplete statements. The third statement is x minus 2 is greater than or equal to 9. This is a variable expression, so without knowing the value of x, we can't definitively say if it's true or false. It depends on what x is. Next, we have is 1 a prime number. Well, 1 is not considered prime because prime numbers are defined as having exactly 2 distinct positive divisors, and 1 only has 1. So this statement is false. Finally, all octagons have 8 sides. That is true, as it's a basic geometric fact. This table helps us understand how to evaluate statements by considering their content and the logic behind them. The key takeaway here is that some statements are straightforward, like the octagon fact, while others depend on specific details, like the value of x. Recognizing whether a statement is true, false, or neither is fundamental to logical reasoning and critical thinking in mathematics. This connects to the broader theme of analyzing statements carefully and understanding their validity before jumping to conclusions. Let's take a closer look at quantifiers. Quantifiers are words that tell us about the amount or quantity of something. They help us specify whether we're talking about a few, some, many, or all of something. Understanding quantifiers is crucial because they allow us to be precise in our communication. For example, saying some students versus all students makes a big difference in meaning. In the context of language and grammar, quantifiers help us add clarity and detail to our sentences. They connect to the overall theme of effective communication. By choosing the right quantifier, we can convey exactly what we mean. So remember, quantifiers are small words with a big impact. They guide our audience's understanding by indicating amounts clearly and accurately. All right, let's take a closer look at some of the key quantifiers we use in logic. First, we have SOME. This term is used when we want to show that at least one object satisfies certain conditions. It's a way of indicating that the condition isn't just true for none or all, but for one or more specific objects. Then we have all. This one is a bit more comprehensive. It shows that every object in our domain satisfies the given conditions. When we say all, we're emphasizing universality, no exceptions. Both of these words are essential because they help us specify the quantity of objects we're talking about. They give us a way to precisely communicate whether a property applies to just some objects or to every object in our set. Understanding these quantifiers is fundamental because they form the basis for making clear, accurate statements in logic and reasoning. They help us connect our specific conditions to the broader context of the discussion, making our arguments more precise and meaningful. All right, let's take a look at this slide. First, we see the statement that all perfect squares are more than 0. This makes sense because perfect squares are numbers like 1, 4, 9, 16, and so on, which are obtained by multiplying an integer by itself. Since multiplying any real number by itself results in a non-negative number, and in the case of perfect squares, it's actually always positive, except for the special case of 0, which isn't a perfect square in this context. But here, we're emphasizing that perfect squares are greater than 0, highlighting a key property of these numbers. Next, we have the number 2 and then 1. These might seem like a bit of a jump, but they serve to introduce some basic examples or to set up comparisons in the larger context of the presentation. Moving on, the statement that some even numbers are divisible by 4 is an important reminder about divisibility rules. While all numbers divisible by 4 are even, not all even numbers are divisible by 4. For example, 6 is even but not divisible by 4, whereas 8 is both even and divisible by 4. This helps us understand the relationship between these different categories of numbers. Finally, the statement that all cats have 4 legs might seem a bit out of place at first, but it serves as an example of a universal statement, something that's true for every member of a certain group. In this case, the group is cats, and the property is having 4 legs. It illustrates the concept of universal statements in logic, which is a key theme in this presentation. Overall, this slide connects various logical and mathematical concepts, from properties of numbers to universal statements in categorization. It's about understanding how certain properties hold true across entire groups or sets, which is fundamental to logical reasoning and mathematics. Now, let's move on to operations on sets. In this section, we'll explore how sets can be combined and manipulated using various operations. These operations are fundamental in understanding how sets relate to each other and are key tools in many areas of mathematics and computer science. First, we'll look at the union of sets, which essentially combines all elements from both sets, removing duplicates. Think of it as putting all items together into one big collection. Next, we have the intersection, which finds the common elements shared between sets, those that belong to both. This is useful when we're interested in what sets have in common. Then there's the difference operation, which gives us elements that are in one set but not in the other. It's like subtracting one set from another. Finally, we'll touch on the complement, which includes all elements not in a particular set, relative to a universal set. Understanding these operations helps us analyze and organize data more effectively, and they tie back into the overall theme of how we can structure and interpret collections of information. So, grasping these concepts will give you powerful tools for problem solving across many disciplines. Now let's look at an example involving negation. Here we have not sign P, which means not P in this case. P states that 2 is an even number, which is true. So not sign P, 2 is not an even number, is actually false. This highlights a key point. The truth value of a statement can change simply by adding the word not. Negation is a fundamental concept in logic because it allows us to reverse the truth value of any statement. If something is true, its negation is false, and vice versa. Understanding this helps us analyze and construct logical statements more accurately, especially as we explore more complex logical expressions. So remember, adding not flips the truth value, which is essential when working with logical statements and reasoning through different scenarios. Let's take a closer look at the concept of a compound statement. A compound statement is essentially a combination of two or more simple statements joined together. These are important because they allow us to express more complex ideas by linking simpler ones. Think of it as building a more detailed thought by connecting multiple statements. The key point here is understanding how these statements work together logically. When we join statements, we're often using logical connectives like and, or, if, then, and if and only if. These connectives help us specify the nature of the relationship between the individual statements. Connecting this to the overall theme of logical reasoning, compound statements enable us to analyze more nuanced scenarios and make more precise conclusions. They are fundamental in constructing arguments, designing logical circuits, and formulating algorithms. So, grasping how compound statements function is crucial, because it deepens our understanding of how complex logical systems are built from simple components. This understanding will serve as a foundation as we explore more advanced topics in logical analysis and reasoning. A compound statement is formed when two statements are combined using the words or and. This means that instead of thinking about each statement separately, we look at them together as a single, more complex statement. The key point here is that these connectors, or and, help us build more meaningful expressions in logic, allowing us to express relationships between different statements. When we say and, we're saying both statements are true at the same time, while or indicates that at least one of the statements is true. Understanding how to form and interpret these compound statements is essential because it helps us analyze more complex logical situations and connect ideas more effectively within our overall logical framework. Let's take a closer look at the conjunction, specifically the and operator. In this table, we see how P and Q interact when combined with and. When both P and Q are true, the result of P and Q is also true. However, if either P or Q is false, then P and Q is false. This is a crucial point because it highlights that the and operator only yields true when both conditions are true. Conversely, if either one is false, the entire statement is false. This concept is fundamental in logic and helps us understand how conditions combine in more complex statements. Remember, the and operator insists on both conditions being satisfied for the overall result to be true. This aligns with the broader theme of how logical connectives shape our reasoning and decision-making processes. All right, let's take a closer look at the disjunction, or the or operation. On this table, you can see the different possible truth values for P and Q, and what the result of P or Q is in each case. The key point here is that the OR operation is true if at least one of the operands is true. So, when both P and Q are true, the result is true. That's straightforward. If P is true but Q is false, the result is still true. Similarly, if P is false but Q is true, the result remains true. The only time the OR operation results in false is when both P and Q are false. This table really highlights the inclusive nature of OR. As long as one condition is true, the whole statement is true. This concept is fundamental because it shows how logical operators combine conditions, which is essential for building complex logical expressions in programming, mathematics, and reasoning. So, understanding how OR works helps us see how different truth conditions influence the overall outcome in logical systems. All right, let's take a closer look at this slide. We start with the statement P or Q, which means either P is true, Q is true, or both are true. Now, moving to the next line, we see -6 - 1, which is marked as false. And that's because -6 is not greater than -1. So in this case, this specific comparison is false. Next, we have the statement Q, which indicates that Q is true in this scenario. Then, the slide shows false, reflecting that the previous statement or condition isn't true. After that, we see P and Q, which is a logical conjunction meaning both P and Q need to be true for the entire statement to be true. Following that, there's a general statement. All even numbers can be divided by 2, which is marked as true. This is a fundamental property of even numbers. Any even number can be evenly divided by 2 without a remainder. Finally, the slide mentions examples, implying that we're about to examine specific instances. The key points here are understanding how these logical operators, or, and, work, and recognizing that some statements are true while others are false, depending on the values involved. This ties back to our overall theme of evaluating logical expressions and understanding their truth values in different contexts. Now, let's take a moment to consider the implications of what we've discussed. First, understanding these key points helps us see how they can directly impact our strategies moving forward. It's important to recognize the broader effects, not just on our immediate projects, but also on the overall industry landscape. By grasping these implications, we can better anticipate challenges and opportunities that might arise. Ultimately, this insight ties back to our main theme of adapting and innovating in a rapidly changing environment. Keeping these implications in mind will guide us to make smarter, more informed decisions as we progress. Now let's take a closer look at the structure of a logical statement. In this context, Q is what we call the consequent, the result or outcome that follows. P, on the other hand, is the antecedent, which is the condition or premise that leads to Q. So, when we say, if P then Q, we're establishing a relationship between these two parts. This form is fundamental because it helps us understand how certain conditions can lead to specific outcomes. Think of it as a cause and effect relationship, where P is the cause and Q is the effect. In our overall discussion of logical reasoning, this structure, if P then Q, serves as the building block for more complex arguments and proofs. Recognizing this pattern allows us to analyze arguments critically and understand the flow from premises to conclusions. So remember, P is the antecedent, the condition, and Q is the consequent, the result, forming a simple but powerful logical connection. Let's look at this example. Here, the antecedent is that x equals 4, which is the initial value we're considering. When we cube that value, so x cubed, we get 64. This shows the consequence of our original statement. The key point here is understanding the relationship between the antecedent and the consequent. If x cubed equals 64, then must be 4. This is what we call a conditional statement. If the first part is true, then the second part follows. It's important to see how the example illustrates this connection clearly. This concept ties into our broader theme of understanding logical relationships and how to interpret these kinds of mathematical statements accurately. All right, so let's take a look at this example. The statement here is, I will play football. Now, the key point is to understand how this relates to the condition about the weather. We have a conditional statement. If the weather is fine this evening, then I will play football. In this case, the part that comes after if, which is the weather is fine this evening, is called the antecedent. Think of it as the cause or the condition that has to be true for the next part to happen. The part that follows then, I will play football, is called the consequent, or the result that depends on the antecedent being true. So, when we analyze implications like this, our goal is to identify these two components, the antecedent and the consequent. Recognizing this structure helps us understand how different statements are connected logically. It's a fundamental concept in logic because it shows us how one statement depends on or leads to another, which is essential for clear reasoning and argument building. Remember, in the overall theme of our presentation, understanding implication and how to identify these parts allows us to analyze arguments better, make predictions, and understand the flow of reasoning more clearly. Now, let's take a closer look at biconditional statements. These are a bit different from the conditionals we've discussed before. A biconditional statement essentially says that two statements are logically equivalent, meaning that both are true or both are false at the same time. We usually write this as if and only if, often abbreviated as if. This phrase is key because it captures the idea that the two statements have a two-way relationship. For example, if we say, if and only if B, we're saying that A is true exactly when B is true, and vice versa. Understanding biconditional statements helps us see the logical connection between statements more clearly, which ties into the overall theme of understanding logical relationships. They are especially useful in proofs and definitions, where establishing equivalence is crucial. So, grasping biconditionals deepens our understanding of how statements relate to each other in logical reasoning. Now let's look at this slide which shows two statements. If P, then Q, and B, if Q, then P. When we combine these two implications, we get a special kind of statement called P if and only if Q. This is a compound statement that contains both directions of implication. What's really important here is to understand that P if and only if Q means that P implies Q, and simultaneously, Q implies P. In other words, these two statements are interconnected and equivalent. This concept is key because it helps us establish a strong logical connection between P and Q when we say P if and only if Q. We're saying that both conditions hold true together. Either both are true or both are false. So, in the context of the overall presentation, recognizing this two-way relationship is crucial for understanding equivalence in logical statements, and how we can use such relationships to build more complex reasoning structures. Let's look at these logical statements. First, we have if Q, then P. This means that whenever Q is true, P must also be true. Then there's if P, then Q, which indicates the reverse. Whenever P is true, Q is also true. When both these conditions are true at the same time, we say P if and only if Q. This phrase highlights that P and Q are logically equivalent. They always share the same truth value. An example of this could be, you will get a discount if and only if you are a student. Here, being a student and getting a discount are perfectly linked. They happen together or not at all. Understanding this equivalence helps us see how certain statements are interconnected, which is fundamental in logical reasoning and forming solid arguments. All right, let's talk about the homework for this session. This is homework 7, and it's designed to reinforce what we've covered today. The key points here are to thoroughly understand the concepts we've discussed and to think about how they connect to the bigger picture of our overall theme. I want you to approach this homework with a conversational mindset. Think of it as a way to deepen your understanding rather than just completing an assignment. Remember, the most important concepts are the core ideas we've emphasized. Understanding the principles, applying them practically, and seeing how they relate to real-world scenarios. By engaging with this homework, you'll be better equipped to see the bigger picture and integrate these ideas into your broader knowledge base. So, take your time, reflect on what we've learned, and make those connections clear. All right, let's take a closer look at this slide. Here, we see references to specific pages and problems, such as PG 98 No. 1 and 2, and PG 96 No 1 and 2. These are important practice exercises that help reinforce the concepts we've discussed so far. The numbers 3 and 4, along with the subpoints of B, C, and D, likely refer to different sections or parts within those exercises, or perhaps different problem types. The key takeaway here is that practicing these problems is essential for mastering the material. They serve as practical applications of the theories we've covered, allowing us to see how the concepts work in real problems. And don't forget the homework assignment at the bottom. It's a reminder to review these exercises thoroughly and ensure you understand each step. Connecting these practice problems back to the overall themes of the presentation helps solidify your comprehension and prepares you for more advanced topics ahead. Let's take a moment to consider the implications of what we've discussed. Firstly, understanding these key points really helps us see the bigger picture and how they fit into our overall strategy. It's important to recognize that these implications can influence decision-making, shaping how we move forward. By grasping these concepts thoroughly, we can identify opportunities for improvement and anticipate potential challenges. This, in turn, allows us to adapt more effectively and make more informed choices. Ultimately, these implications underscore the importance of integrating this knowledge into our broader goals, ensuring that we stay aligned and proactive in our approach. All right, let's look at this example. If x equals -5, then what is 2x minus 7? Well, first, I substitute -5 for x, so 2 times -5 gives me. Next, I subtract 7 from which results in. So in this case, the statement is true because the calculation confirms it. Now, shifting gears a bit, I want to talk about the concept of the converse in logical statements. The original statement is, if P then Q. The converse flips that around and says, if Q, then P. It's important to understand this because the truth of the original statement doesn't always guarantee the truth of its converse. This idea ties back to our overall theme of logical reasoning and understanding the relationships between statements. Recognizing the difference between a statement and its converse helps us analyze arguments more carefully and avoid assumptions that might lead us astray. Now, let's take a moment to look at arguments. This slide highlights the key points we need to consider when evaluating different perspectives or solutions. First, it's important to thoroughly understand each argument, but we should do so in a conversational way, making it easier to connect with the ideas. We want to highlight the most important concepts to ensure they stand out. Remember, these arguments are directly linked to our overall theme of making informed, balanced decisions. By analyzing each point carefully, we can see how they support or challenge our main objectives. So, as we go through, keep in mind how each argument fits into the bigger picture and helps us move forward with confidence. So let's look at this slide. It states that all quadrilaterals have 4 sides. That's a key property of quadrilaterals in general. Now, since a rhombus is a type of quadrilateral, it must also have 4 sides. This is a simple but important logical step, because if the broad category quadrilaterals all share this feature, then the specific type, the rhombus, shares it too. This is a good example of how we can use basic properties to draw conclusions about specific shapes. It highlights the importance of understanding the defining features of geometric figures, which helps us reason more effectively. By connecting the general property to the specific case, we're reinforcing the overall theme of logical reasoning. Remember, understanding these foundational concepts builds a strong base for more complex geometric ideas. All right, let's take a closer look at this slide. We start with the statement C is B, which is our conclusion. Then we see C is A, indicating a different relationship or claim about C moving on. Premise 2 states that all A is B, meaning every A falls under B and premise 1. Well, that's the foundation of our argument, which isn't explicitly shown here but is crucial for the logical structure. This slide is illustrating an argument form called a syllogism. Specifically argument form, the key idea here is how different premises connect to lead us to a conclusion. The forms of arguments part reminds us that understanding these structures helps us evaluate the strength of our reasoning. By analyzing these components, we see how logical connections work. The main takeaway is that, with the premises, such as all A is B, and others, we can logically derive conclusions like C is B. This is a fundamental concept in logical reasoning and critical thinking, which ties back to our overall theme of understanding how arguments are constructed and evaluated. All right, let's walk through this slide. We're looking at an example of how to make a conclusion based on premises. First, notice the premise that 78 can be divided by 2. This is a factual statement that sets the stage. Then, the conclusion drawn from that is that 78 is an even number. The key here is that even numbers are defined as numbers divisible by 2, which is why this conclusion makes sense. Next, we have premise 2, which states that all even numbers can be divided by 2. This is a general rule that applies to every even number, including 78. And premise 1 simply states that 78 is an even number, based on the previous evidence. Putting it all together, the overall idea is that from the premises, 78 being divisible by 2 and all even numbers being divisible by 2, we logically conclude that 78 is an even number. This example highlights the importance of premises and how they support a logical conclusion, which is a fundamental aspect of constructing strong arguments. Now let's look at the key points here. First, we see that Q is true. This is important because it connects directly to our conclusion, which is that P is true. Next, we have premise 2, which states that if P, then Q. This is a conditional statement, meaning that whenever P happens, Q must follow. Then, premise 1 simply asserts that P is true. When we combine these premises, we're applying a classic form of logical reasoning called modus ponens. This argument form allows us to conclude that since P is true, and if P then Q is true, Q must also be true. Finally, the overall point here is to understand how this structure of reasoning works. It's a fundamental way we make logical inferences, by affirming the antecedent to arrive at the consequent. Recognizing these forms helps us evaluate arguments more critically and understand their validity within the broader theme of logical reasoning. All right, let's look at this example. We have an equation, x plus 4 equals 10. This is our starting point. The conclusion here is that x equals 6. Now, to connect these, we have a premise. If x equals 6, then x plus 4 equals 10. And of course, the first premise is simply the example itself, showing the form of the argument. What we're seeing here is a clear example of how arguments are structured, especially in logical reasoning. The initial statement sets the problem, the conclusion follows logically, and the premises serve as the supporting reasons that connect the two. This kind of structure is fundamental in understanding how we build valid arguments, whether in math, science, or everyday reasoning. It highlights the importance of premises and how they lead us to logical conclusions, which ties right into the broader theme of evaluating argument validity. Let's take a closer look at this argument form, known as modus tollens. The key idea here is that if we know if P, then Q, and we also find that not Q is true, then we can conclude that not P must also be true. In this slide, we see that the conclusion is not P is true, which follows logically from the premises. The second premise states, if P, then Q, establishing a conditional relationship between P and Q. Premise 2 confirms that the conditional holds, and the assertion that not Q is true serves as evidence that P cannot be true. This pattern is a common and powerful form of logical reasoning, often used to disprove hypotheses by showing that their consequences don't hold. Understanding modus tollens helps us evaluate arguments more critically, especially when trying to determine what must be false if certain outcomes are not observed. Overall, this slide highlights how logical structures like these provide a clear framework for assessing the validity of arguments based on their premises. So in this slide, we're seeing an example of an argument that might seem straightforward, but it's actually invalid. The statement here is that ABCD is not a square. From that, the conclusion is that ABCD does not have 4 sides. Now, what's important to notice is that the argument is structured with premises and a conclusion. Premise 2 states that if ABCD is a square, then ABCD has 4 sides. Premise 1, which is the initial statement, says ABCD is not a square. The key point here is understanding what this argument is claiming and whether it holds logically. Just because ABCD is not a square, does that necessarily mean it doesn't have four sides? Not necessarily. The argument tries to conclude that ABCD does not have four sides based solely on the fact that it's not a square, which is a logical misstep. This example helps us see how important it is to analyze the structure of arguments carefully. It shows that even if the premises are true, the conclusion might not follow logically, especially if the reasoning isn't valid. In the broader context of our presentation, this highlights the significance of understanding different forms of arguments and recognizing when an argument is valid or invalid. It's a crucial skill in critical thinking and logical analysis. Now, let's talk about recognizing the argument form and completing the argument according to that form. This is a crucial skill because understanding the underlying structure of an argument allows us to evaluate its validity more effectively. When we identify the form, we can see how the conclusion logically follows from the premises, or where it might fall apart. The key here is to first analyze the argument to see what kind of logical structure it follows, whether it's modus ponens, modus tollens, or perhaps some other form. Once we've done that, we can then complete or build the argument in a way that preserves that logical form. This helps us ensure that our reasoning is sound and that our conclusions are well supported. Remember, recognizing the form isn't just about labeling, it's about understanding how the parts connect. This understanding is essential as it ties into the overall theme of critical thinking and logical analysis. By mastering this, you'll be better equipped to construct strong arguments and also to identify weaknesses or fallacies in others' reasoning. Let's look at the conclusion that x equals 16. This is based on a logical chain of reasoning involving premises. Now, premise 2 is missing here, but what we do see is premise 1, which states that if x minus 6 equals 10, then must be 16. This shows how a conditional statement can lead us directly to a conclusion. In the next example, we see a conclusion about the sum of interior angles in a triangle, which is 180 degrees. Again, premise 2 is left blank, but premise 1 reminds us that all triangles have interior angles that sum to 180 degrees. The key point here is understanding how premises build up to support a conclusion. When we have a clear logical structure, like in these examples, we can confidently determine the truth of the conclusion based on the premises. It's essential to recognize the importance of each premise and how they connect to form a solid argument, especially in geometry and logical reasoning overall. Let's take a look at this homework slide, which covers exercises 4.5, numbers 2, 3, 4, and 5. These problems are designed to deepen our understanding of the concepts we've discussed so far. As you work through these, focus on applying the key principles we've covered, like setting up the correct equations and carefully analyzing the data. Remember, these exercises are a great way to reinforce your learning and ensure you can handle similar problems on your own. Keep connecting these problems back to the overall themes of the presentation, like problem-solving strategies and critical thinking. And don't forget, working through these thoroughly will prepare you well for any related assessments or real-world applications. Let's take a moment to explore mathematical reasoning. This is a crucial skill because it helps us understand how to approach problems logically and systematically. When we talk about mathematical reasoning, we're really focusing on how we draw conclusions from given information, how we make inferences, and how we construct sound arguments. This skill is essential not just in math, but across all areas of problem solving. It connects to the overall theme of developing critical thinking and analytical skills, which are vital in many real-world situations. By honing our mathematical reasoning, we improve our ability to think clearly, make decisions, and solve complex problems effectively. Now, let's explore the concepts of deduction and induction, which are fundamental to mathematical reasoning. Deduction is about starting with general principles or known facts and logically working towards a specific conclusion. It's like following a clear, step-by-step path where each step follows necessarily from the previous one. Induction, on the other hand, involves looking at specific examples or cases and then making a generalization based on those observations. It's a bit more about pattern recognition and forming hypotheses that can later be tested or proved. Both methods are crucial in mathematics. Deduction helps us verify truths with certainty, while induction allows us to formulate conjectures that guide further exploration. Connecting this to our overall theme, understanding how these reasoning types work enhances our ability to develop rigorous proofs and to think critically about mathematical problems. They're the tools that help us move from assumptions to conclusions, whether through logical necessity or pattern-based inference. Now let's take a closer look at induction. Induction is a process of making a specific conclusion based on a given general statement. Essentially, from a broad idea, we narrow down to a particular case. It's like observing a pattern and then applying it to a specific situation. On the other hand, deduction works in the opposite way. Deduction involves starting with a general statement or principle and then reasoning down to a specific conclusion. Both methods are fundamental in reasoning and logic, but they serve different purposes and follow different paths. Understanding these two ways of reasoning is crucial because they form the backbone of how we analyze information and draw conclusions in various fields. Induction helps us build general theories from observations, while deduction allows us to test those theories by applying them to specific cases. So, in summary, induction moves from the specific to the general, and deduction moves from the general to the specific. Both are essential tools for effective reasoning and decision-making. Today, we see that all students in Form 4X are present. Specifically, David, who is a student in Form 4X, is also present today. From these observations, we can conclude that David is present today. This example highlights how we can use logical deduction to arrive at a conclusion based on the given facts. It's a simple yet powerful way to understand how evidence leads us to logical outcomes. Now, let's talk about a process called induction. This is essentially about making a general conclusion based on specific cases. In other words, when we observe particular examples or instances, we try to identify a pattern or a principle that can apply more broadly. It's like noticing that every time I leave my house without an umbrella, it rains, and then concluding that leaving without an umbrella often leads to getting wet. The key point here is that induction moves from specific observations to general ideas. It's a fundamental way we reason in everyday life and in scientific inquiry. Connecting this to our overall theme, induction helps us build broader theories or hypotheses from specific data, which is essential for developing understanding and knowledge. It's a powerful tool, but it also requires careful attention to ensure our generalizations are valid and well supported by the evidence we've gathered. So, in conclusion, all students in Form 4X like physics. For example, Carol is a student in Form 4X, and she likes physics. Elise is also in Form 4X, and she likes physics too. And Amy, another student in the same class, likes physics as well. This shows us that the majority of students in Form 4X share a positive attitude towards physics. It's great to see such enthusiasm and interest in the subject among the students. This positive attitude can really help them succeed and enjoy their learning journey in physics. Now, let's bring everything together by looking at the overall structure of reasoning. At the top, we have summarized reasoning, which is like the big picture overview that ties all the pieces together. Moving down, we see induction, which is a method of reasoning where we generalize from specific examples to broader conclusions. Then, there's deduction, which works in the opposite way, starting with general principles and applying them to specific cases. And finally, at the most detailed level, we have the specific reasoning, where we analyze particular instances to support our conclusions. Recognizing how these different types of reasoning connect helps us understand how we build strong, logical arguments in critical thinking and problem solving. This slide emphasizes that understanding the hierarchy and relationship among these reasoning types is key to mastering effective reasoning strategies.